All right, here's a breakdown by weight of the machine. So basically the sticky notes here are the measured weight. And this is the entire mechanical structure of the machine, plus the actual, just the spindle body, but not the spindle motor. This is basically as far as I've been able to disassemble the machine without a couple of tools I'm waiting on. So 44 pounds there, that's basically half. It's actually like exactly half the weight of the machine. Next up we have 16 pounds, which is basically everything else. It's the two plastic side end plates, all of the plexiglass, and all the electronics, the steppers, the balance of all the bolts that I didn't take out. A couple of the spindle aluminum pieces are in there just because I was able to remove them from the first part. So that's 16 pounds. And then the big whopper here is that this is just the stainless steel outer pieces, and they weigh 29 pounds. So this is the back cover, the front cover, the top plate, I'm sorry, this is the bottom plate here, the top plate, and then I think there's one other, yeah, there's one other piece there, the back plate. But man, when 29 pounds of your machine is aesthetic, and your machine only weighs 90 pounds, that's a third of the weight of the machine is purely aesthetic stainless steel. And gosh, this stuff is super, super thick and for no reason. This small piece just starting here, this could be half the thickness, and you would never know as a customer. It would be 100% as solid or whatever. The bottom plate doesn't, I mean, that could be half the thickness too. It's not doing anything. It's just glued to the bottom. These pieces are like 5 and 6 pounds a piece. This back cover here, it's 20, I actually don't know the weight of the back cover, sorry. But you can see they actually made it slightly thinner, but it's still about, it could be, I don't know, 70% of that thickness. So it's, why the design decision to make that 29 pounds, particularly because this is 90 pounds shipped, and it's just shipped UPS, a third of their weight. And more notably, what makes it more than 70 pounds, which makes UPS not want to deliver it, is just aesthetic. And you could make all of this thinner. You could make that weigh 8 pounds, easy. And then you'd have 44, that'd be 52, and that would be 68 pounds. And you wouldn't get the UPS surcharge, and UPS wouldn't not want to deliver it, as has happened in my case. So, anywho, seems like a third of the weight of the machine is purely aesthetic. The chassis itself is about half the weight of the machine, and the balance, everything else, the electronics, the bolts, and I'll kind of just take this out so you can see what's in here. It's the, this piece, this part of the spindle motor. This is the square angle bracket that comes on there. You got the feet, a couple other little spindle pieces, the actual motors, and then just all of the screws and whatnot. That's all of the weight. The only thing I haven't included is the actual box, the little shipping box that comes with it, and that probably weighs more than a pound, but that just contains, the power cord and whatnot. As I'm putting this back together, I realized why there's actually one bolt that's a different color. That's an indicator of where the rotation point is as we reassemble this tray. What they've done here, these are both the same screw thread, but this is actually a wider insulating standoff so that the bolt has a room to wiggle, basically. Whereas on this side here, the insulator here is actually thicker, and the bolt does not actually slide in. You actually have to thread it. And what that does is it allows you to have a central point to rotate around, so that as you try and square this table, you aren't, pushing the table, you aren't laterally translating it, you're only rotating it about that point. So with this screw in, you can see that, you might be able to see that the table rotates about that point. So that's why they do the one silver screw there. There's nothing with the screw that's unique, it's just to indicate to the assembler that is where we're rotating it around. Yeah, so the way we're gonna square this is we're gonna take a parallel, which I don't have a parallel sitting here, but I'll just show you what I'm going to do representatively. You're going to take a parallel, again, this is not a parallel, and once we screw these screws down, they'll be slightly below the flush there, and that allows us to put this here, and then we'll basically have to install a tool and tram it along that edge. That's how we'll make sure this is straight. This is the actual piece that's assuring that we are straight there. So yeah, I'm gonna put this back together, and we're gonna play around with the actual stepper torque. All right, I've got Bantam's electronics set up here. I'm using their power supply. It's outputting 24.13 volts. That's not really changing, nor would I expect it to. It's a constant voltage power supply. Their device basically goes through this power board and then into here. I've got the spindle portion unplugged because I'm just characterizing the steppers right now. And you can see that our idle power is about 1.6 watts, and that's just the power to run, you know, the LEDs and this Atmel and any kind of, you know, voltage supervisory stuff here. The steppers are not energized right now. I haven't opened the device and enumerated it yet. So we're gonna open up the device here. And so again, we're using 1.6 watts now. Write that down. And we're gonna start homing. And when we're in the homing cycle, it's actually low power. It's pulling basically 200 milliamps, which is 4.5 watts. And so, interestingly here, the limit switches, they don't have any kind of check that the limit switches are tripping and untripping when they should. So all you gotta do is just push them here. You know, even Gerbil basically has a timeout basically if the switches don't switch soon enough, or there we go, I think we're good. Or if they switch too soon or whatever, they're actually looking to make sure the switch is switching at the correct time. So at this point, we've homed the machine, and again, while homing, we're pulling 200 milliamps. Oops, 200 milliamps times 24.13. So that was 4.8 watts. And now at idle, it's 470 milliamps, which is 11.34 watts. And when I move, so if I open a console, one of my first thoughts was, well, maybe they just have a low power mode. Now, one thing I want to point out is that stepper motors pull the maximum amount of power when they're idle. And so if you're not moving and you can turn the power down then, just keep your holding torque, then you actually save a lot of power and your motors won't get as hot. And we'll come back to heat there. So what I'm going to do here is I'm just going to do an F100 G1, so we're going to move it 100 units, and we're going to do per minute, and we're going to do X200, Y200, and then Z200. So we're going to just move all three motors simultaneously just to categorically and unequivocally say that there is no power increase or decrease here. So with that motion here, we were pulling 410 milliamps, and again, that's expected behavior because, 410 negative 3 times 24.13, that is 9.89 watts. And again, steppers pull less power when they're moving. They pull the most power when they're stationary. So all this is to say that we're only driving these steppers at 9.89 minus 1.6 watts divided by 3 because there's 3 of them. So we subtracted the idle power and then we divided by 3. We're only running 2.76 watts through each stepper motor. That is not a whole lot of power, and it's why these stepper motors have basically no holding torque and essentially no stationary torque too. I'm actually just rotating this by hand. Okay, so how do they drive these harder? Well, unfortunately, you can't. The electronics bay here has no fan, and these DRV8818s, so these can drive about 2 amps per coil, which when you do the math, actually, there's some the currents don't equate properly because it's a 2 amp chopper, and so you're not always sitting there at 2 amps. But generally, just summarizing it here, you can push these DRV8818s to where they're pushing about 24 watts per stepper. That's a lot of power. So they're going to overheat, and so typically what you're going to do is you're going to run them a lot lower than that, maybe at like 10 or 15 watts. Too many details there, sorry. All that is to say is that without a fan in here and without a custom PCB, there's no way that Bantam can fix this problem, the problem of having no torque. I want to show you for reference, this is a board that I've done. This is using the same DRV8818s. You can see 1, 2, 3, 4, 1, 2, 3, 4. And these are driven at 50 watts idle for 4 steppers. So I'm using, I don't do math, sorry. I'm pushing 12.5 watts per stepper maximum, basically. And in addition, I actually have the circuitry that I mentioned that actually drops the power down to about half of that. So at idle, they're only pushing about 6 watts. So at idle on this PCB, I am pushing twice the current as these are doing, twice the power. When I'm moving, I'm doing 4 times the power, and that's why there's a ton more torque on this board. Now notice though that I have these 2 heat sinks here. These are basically ground plane heat sinks that are designed for like a D-squared pack or whatever, but I'm just using them to pull the heat out of the ground plane. I'm also, with a fan, blowing air through a channel cavity on this at about 150 linear feet per minute to keep these cool. If this fan turns off, this board will overheat, and the board can detect that or whatever, but all that is to say is that without a fan again in the Bantam, this board is never going to be able to push the power. So another thing, just to drive this point home, this is the stepper motor that I use in a design that I have. Look at the difference in height there. So this stepper motor, I'm pushing 4 times the power through versus that one, which is, you know, 60% again is tall. So it's very odd why they're using a stepper that's so big there, because these steppers can handle quite a bit more power than this one is designed for. So all that is to say here is that the stepper motors in this device, the way their architecture works, the way some of the engineering decisions that they made, there's no way they can control and push any more power in these steppers. Now, one thing I'll point out, I've said a few times, there's no fan in this device. There is actually a fan in this power supply. It's temperature controlled, and it's only controllable by this power supply. And it only cools the power supply as well. As you can see, the air outflow here is basically, there's a few channels right here, but mainly the outflow is coming out this side basically. But because of the way this is installed in the unit and the way the cover covers over it, that air is basically blowing. It's never going to blow across this PCB is all I'm trying to say. So you're not cooling. There's no way to cool this PCB. And because it has no heat sinks, because there's no fan, all of those things add up. And it basically says that you can't push more power here, in summary. These DRV8818s will run really hot. They'll work pretty well. These, I'm touching them, they're not that warm. They're probably 35 degrees C. So it's certainly possible that they could increase the power slightly, but they're not going to get anywhere near the 15 watt range that really this motor should have, this machine should have, the 15 watts per stepper. Whereas right now they're running it at less than 3. What was the number? It was 11.34 minus 1.6 at idle divided by 3. So they're 3.25 watts at idle, and at even a minor motion, I was moving at 100 millimeters per minute, minus 1.6 divided by 3. 2.75, so they're consuming between 2.75 and 3.25 watts, depending on whether or not they're stationary or idle, whereas they should be consuming 15 watts, so 5 times more power to get their holding torque. And to be honest, because these steppers are bigger, they could push them harder. The steppers themselves are never going to be the problem. It's the control architecture here. One of the problems with an off-the-shelf solution like this is that if it doesn't support the feature you want, you don't get the feature, and that's the case here, and that's why, as we'll see, I'm going to put a Coke can in this machine when I reassemble it. I don't think we're going to even be able to crush a Coke can, which is sad. All right, let's look some more at the software firmware side of this. So one of the things I want to point out, this has an 8 GB SD card in it, and I thought maybe they were storing something there. I don't know what. All it has is this persist persist.2 file. It's not text by default, but it's obviously just, I think it's a persist.binary or whatever. But it's only 4 kilobytes. There's really not a lot of data there. I guess it's writing something there. Maybe that's for future support. Obviously, they've stuck an 8 gig card in there, so they mean it. All right, let's play around with TinyG here. One of the things I just want to say from the get-go is that TinyG is GPLv2 is their license, which means if this is modified in any way, it must be offered for download on the manufacturer's website. I did not find a download on Bantam's website, so under the terms of that license, I would presume they haven't modified it. We'll see if that's true or not. I've got the help page open here. I've used TinyG. I haven't used it in a bit. I've mainly been in Gerbil, which is very similar. Gerbil does not support JSON. If that doesn't mean anything to you, then don't worry about it. So this is just a standard serial port. So if you just list the devices, and we'll start with tty.star, which is for USB modems. There's our device. It's USB modem 14.2.11. And so we're going to just connect to that. So we'll do screen, and then it's device, and it's TTY. I know you can hit tab, but I'm not going to. It's USB modem, and then we just type this number in, 14.2.11, and then we need to hit the baud rate, which is 115.200. So there we are. We're hooked up to the device now. See if I can make this text larger. Yeah, we can. Let's do a status report, and so it returned. Oh boy. Well, the formatting's a bit odd. I could play around with that in this putty window. I'm not going to. This is decent enough. Cancel motion. You know, so we just got a bunch of things. Machine, feed, hold, state. Let's see if we can get some firmware build info. So that would be $FB. And firmware build is 101.11. I'm writing this down. I haven't actually looked at it. So we're going to do $FV for the version. And, oops, I did FW. $FV is 0.99. So they're running 0.99 of TinyG, presumably. And hardware platform, HP is G2 Core. Yep, so this is running the G2 Core, which is basically the V9 TinyG board here that you see in frame. That's the board they're using. And we'll do hardware version, so that's $HV, which I guess is K. Let's get our system parameters, which is $sys, and that actually spit out quite a bit of data there. Feed rate override, blah, blah, blah. Default coordinate system is 2. So in TinyG, the coordinate systems, 1 is G54, 2 is G55. So they're using G55 for default. Typically you'd start in G54, but you know, whatever, that doesn't, you can start wherever you want, I guess. I want to write that down here real fast. That would be G55 is default. Let's see, the unit, if we just type in a unit here, oops, it didn't like that. A gun, funny, they have a mode for gun. Default G-code units mode is 1, so G21, okay. That is millimeters. I like that it starts in millimeters. I just assumed that it did, I didn't actually know that for sure. Let's see, we've gotten that. Let's see the motor settings. Power level is 0.3. So actually it seems like we might be able to, on this V9 hardware, change our power level. So that's 3PL. So if we say $3PL, we might be able to actually increase the power level here. Interesting, and that's 0.3. So that's a change between the 0.8 and the 0.9 board. So let's look at the motor settings here, and it seems that the power settings are ultimately configurable on this board, on the V9 hardware. What you do is you do $, and then the motor number 1, 2, or 3, and then PL, which is power level. So the default values here, if you just do $M, which is going to give you all the motor commands, You can see that our power levels are 30%. So 30% here. You can see that this board is sitting here. Maybe you can't see that. It's sitting here at about 120 degrees Fahrenheit. Interestingly, the processor itself is quite a bit warmer than I would expect it to be. It seems to be running very quickly. They don't have an idle state or something. But we're more interested in the DRV8818s, which are sitting right here. And they're rolling around 120 degrees right now, which is totally within acceptable values there. So the default values are 0.3, which is 30%. We're going to go to 50%. And to do that, we're going to have to change all three. So we'll do $3 PL equals 0.5. And then we'll do $2 PL equals 0.5. And we'll do $1 PL equals 0.5. And so doing that, we are now pulling 20.4 watts. And we'll give this board a minute here with the no airflow that it has to warm up. But you can see, well, it's actually about the same temperature right now. So it's 120, you know, maybe we haven't waited long enough yet. We're definitely pulling more power. So we were pulling 11 watts and now we're pulling 20 watts in the board there. But it seems like for now, we're able to sink that heat into the PCB. That's gonna obviously change. Sorry, that's out of view. So it looks the same as what I'm trying to say right now. But I think that's gonna change as we continue to soak that board in the heat that it's generating. Yeah, you can see now the temperature has risen a couple of degrees. Really, we should wait a little minute here to, to get valid data. We should probably wait 4 or 5 minutes, but we're not going to do that because what I want to do is step up and see the maximum amount of power this board could provide. What I was saying earlier is that if you do support the low power idle mode, because stepper motors idle at full power and when you move them, they pull less power. If you can actually limit the power at idle, then you don't have to worry as much about the motors overheating. So all that is to say is I want to be pushing 15 watts through these motors, which is what this other PCB I showed earlier is doing, is about 15 watts per motor during motion. And I'm not sure this board is going to be able to do that, but let's see. We're going to do $3 PL equals 0.7, and then $2 PL equals 0.7, and then $1 PL equals 0.7. So we're now driving at 70%. We're pulling 37.5 watts. And so you can see that this board has now gotten very, very warm. 140 degrees Fahrenheit, and that will continue to get worse because we have no airflow. So we've just broken 140 now. And we're only pushing at this point. If we take, I knew that was going to fall. If we take the idle power, which is 1.8 watts, and so we're going to say 37.5 minus 1.8, and we divide it by 3, that is 12 watts per motor. So we actually need to go a little bit higher, so maybe up to 80%. $3 PL equals 0.8, and $2 PL equals 0.8, and $1 PL equals 0.8. Yep, okay. So at this point, we're pulling 46 watts, 0.0 watts at 0.8. So that's basically the 15 watts per stepper that you really need in a desktop CNC machine like this. But also the DRV8818s have warmed up quite a bit. They're now at 155 degrees Fahrenheit. That's going to continue to soak as the board heats up. This is, again, in a completely enclosed container that it has some air venting on the left side for the power supply, but none of the exhaust air is going to be influencing this board. Sitting here on the desktop right now, as this is a much better cooling environment than this board is normally going to be under. I'm lost right now, sorry. Actually, if I flip this the other way, that might be a little bit easier to see. There we go. So yeah, you can see that we're now at we're rocking around 150 degrees Fahrenheit. One thing we're going to see too is that the steppers are going to start to warm up, and so they're 93 degrees Fahrenheit right now. Because they don't have an idle power cut down, when they're sitting here idle, they're going to just be really warm. Because two of these steppers are outside of the enclosure, I guess the X and Y steppers are outside of the enclosure, those can't be warmer than, gosh, what is it, 50 degrees C? If they are, then they're a burn hazard. I think it's 160 degrees, 150 degrees Fahrenheit. I don't remember, somewhere on there. I'd have to look it up. But the limitation remains that these steppers will overheat, or they won't overheat, but they become a burn hazard because they're outside of the machine. And then you can see here that this board is continuing to rock along at about 155 degrees now. And our power supply fan actually just turned on. So we're pulling 47 watts, and we were able to turn the power supply on here, which is fine. It's temperature controlled, but there's none of that airflow is going to cool this PCB down at all. So really the lack of fan inside the Bantam is going to be an Achilles heel as far as the torque in the machine is concerned. So let's go ahead and we'll put these values back to what they to their default values, which $3 PL equals 0.3 and $2 PL equals 0.3. You can actually see the chip cooling down in real time here. So yeah, we just hit 155. So there's definitely a lot of $1 PL equals 0.3. Definitely a lot of latent heat going there. So we just dropped back down to our OEM settings, which are 10.1 watts instead of 46. So we were pushing 4.5 times more power through than the default value there. That board got a little bit toasty. We'll see when we look, when we put the machine back together. I don't think the machine can even crush a Coke can, but maybe it can, maybe it can't. But we'll see. I think it'll be a fun test to see. So I've got this little can here that we'll stick in the machine and see if we can crush it. Again, I think the answer there is no. So yeah, that's stepper motors. That's the power. Bantam definitely has the ability to change the power settings from the kind of abysmal default 10 watts to a higher value. They're certainly not going to be able to push it up to, you know, again, like the 15 watts per stepper that you really would need in a machine like this. But certainly they could push it higher than a 3. So they're not going to be able to get the 5 times more power they need, but they might be able to get 2 or 3, which would be a big help to their machine not sucking on stalling during motion profiles. Now I've disconnected the steppers and I've connected up the spindle. I only have the motor for the spindle hooked up because I'm only characterizing the no load power draw, and we'll then characterize the no load power draw with the spindle attached, so the belt connected to the actual spindle. And finally we'll do a tester using a Prony brake tester specifically designed for testing these brushless DC motors. So we've turned our power on, we've got our power consumption here. Here's the motor controller. Now this is only the motor controller that's doing the beeping there, and the way we can show that is if we unplug this serial connection, like that. Serial's now unplugged. Still does it. So what this guy's saying now, the beep is different, and it's saying, hey, I wasn't able to get the VCC or the serial connection because we unplugged it. But it's just this off-the-shelf, this is actually just like an RC helicopter controller, completely off-the-shelf. I was able to find it online for 25 bucks or whatever. This motor is also just an RC type motor here. So we'll go ahead, we'll top this back off here so we can plug this in. And we'll plug our serial connection back in. Oh, why don't we plug it in? There you go. So here we go, and now we have a serial connection. That's what it's telling you. Our no-load power is a little bit higher now. So before it was 80 milliamps, but we didn't have this controller plugged in. Now it's 110 milliamps, so 0.01. And what we're going to do is we're going to open the Bantam software. Oh, by the way, I'm sure I'm talking louder than normal. I'm wearing earplugs just because these motors get to be very loud, and we're going to run it for a little bit here. So we're initializing. We're going to, I'm going to see if I can get away without homing because I don't have the steppers hooked up, but let's see if we can do the, so we cannot actually do the spindle warm-up without homing. So what we'll do is we'll just trick this again. And you don't need to really care about how you push these because there's no check to make sure that they're happening in a sane way. So I think we're probably good now. Yeah. So we're going to do our warm-up routine. And this should start spinning. So we went from 110 milliamps to 1.08 amps or whatever. So 24 watts, 26 watts or so. So we were using 0.1. This is a slow speed, so we're gonna ramp up in speed. So our idle is 2.65 watts at idle, and this is our. I'm just gonna say speed 1 on their warm-up cycle, and that is 1.08 times 24.13 is 26.06 watts here at whatever this slow speed is again. I don't know what cycle they're using, and I need to just go in there and learn the command, but I just haven't taken the time to figure out how it is that they're blocking me from typing M3 S3000. It's possible that Spindle doesn't support an RPM that slow. We should hook up an oscilloscope. I've got my, as every hacker should, a Rigol TS1054Z that's been hacked. Okay, we're at speed 2. Sorry, we got a little interrupt there. So at the second speed, we're pulling 1.64 amps, which is 39.6 watts. And yeah, so we'll get our Rigol set up while we're waiting on the next speed. Sorry, hit the tripod there. And because this doesn't have Hall sensors, we're not going to be able to just hook up to the Hall sensor. So we're going to have to use the flyback voltage on the transformer, or I mean the spindle, which is just a transformer. We'll set this here dangerously close because I like to roll. And also I want you to be able to see it. Is that still in frame? Yeah, close enough. All right. So we definitely don't want this cable to touch that. Yeah, that's not a good spot. First spot was better. There we go. And we're gonna figure out the RPM, but I warn you, this is going to be a really noisy signal because we're going to be hooking straight up to the FETs. And we need a ground. Oh man, come on, camera. Killing me. Probably better view anyway. This tripod I'm using just has really goofy long legs. Okay, enough complaining there. We're going to grab our ground reference, and I don't know from where. I'm going to grab a jumper. Sorry, all this is on the fly. Hey look, I've just got one sitting there. We're going to grab ground reference here. This is going to be noisy. Obviously you want your ground reference to be shorter, but we're not looking for signal accuracy, we're looking for a signal. And we're going to go to, okay, so another interrupt here. We've got our third speed. This is S3, and it is 1 point, kind of jumping all over the place. We're going to go with 1.93 amps, which is 46.6 watts. There. Again, this is a no-load test condition. We'll do the other 2 test cases as well. This is not going to give us any data by itself, but it will certainly give us data when we take our other measurements. So we're going to hook up here, and we're going to just pick any random phase, doesn't matter which one. And W looks like the easiest to grab onto. So there is our data. And it looks like we're doing, yeah, it's a PWM, so this is just a trapezoidal, but what we'll do is we'll take a screenshot here, and we'll look at our cycle here. So we're going to just look at this high cycle. Well, we should look at the whole cycle here. So we've got 100, 200, 300, 400, 500, 600, 700 microseconds between our phase firings at no load. And so what we'll do now is we're going to place a load on it, and we're going to try and simultaneously look at the current and our frequency dip here. So that's 14 amps. Woo! Wow, we know the speed. So S4 is our last speed, and that is 2.30 amps. Okay, so we pulled with an arbitrary load, we pulled 14 amps. And if we look now, we've got 100, 200, 300, 400, 500, 600, 700, 800, 850 microseconds. So it's possible a closed loop because 14 amps is 14 times 24.13 is 337 watts. Which this power supply is only rated for about 350, but I can tell you from personal experience that you can pull quite a bit more from them. So what we're going to do, that was our first test. We're going to actually put a slightly less load. We're going to try and load this to about 10 amps. Of course, the speed has changed now, so we need to actually grab our new data here. So we've got 100, 200, 300, 400, 500, 600 microseconds at this faster speed. And hopefully we can do this test before it changes again. So we're going to try and get to about 10 amps to a single. So that was about 12 amps. So 12 amps. 14, 12. Sorry, I'm gathering this data quickly. So we've got, we'll start from the same spot here. And we've got 100, 200, 300, 400, 500, 625. Okay, so microseconds. Yes, this is a closed loop spindle. Cool. Try one more. We're going to try to go for that 10 amp value there. Yeah, that's about right. Okay, so again, 100, 200, 300, 400, 500, 625. Yeah. So yes, it's a closed loop spindle. It's completely off the shelf. There's no feedback here. If we change now to look at the serial bus on our white line here, this will probably, it's either going to be a PWM or serial bus. This is a serial bus. Let's see. No, this is PWM. There's no data here. This is literally PWM. So there's no serial bus between the two, which they never claimed to have. So I thought maybe they'd have a data bus. But yeah, this is just a PWM. It's a 28 kilohertz, 29 kilohertz PWM to control the spindle. And we'll see when this stops here in a minute. Presumably 0 kilohertz would be no motion. And just the various methods in between would be the speed. So it's a, let's do our duty cycle. Where is duty? Yeah, okay, I'll have to do it manually. I'm lazy if I haven't exemplified that. So we got 2.5 milliseconds out of 510. So this is a 25% duty cycle. This will be S4. This data is kind of gathered quickly. So, but hey, we can push a lot of power. Now, one thing I probably want to show you is how warm this controller is going to get when we load it. So I'm going to sit here and just load it at about 10 amps. Woo, yeah, it's getting warm quick. Okay, well, it turned. Yeah, okay, well, that was just because it was finished. So, yeah, I guess that's what we've gathered out of that. It is a closed loop spindle, but the closed loop is just all on the hardware here, flying off the shelf. And it can push a lot of power. One of the things I wanted to point out is because there's no power limit here, we can almost certainly, by stalling the spindle out, say if you crash the spindle, we can almost certainly make this power supply turn off. But yeah, let's see how much power we can pull here. My goal is to get this to turn off. There it goes. So we killed the power supply there. The Bantam knows immediately that the machine was disconnected, so at least we know the power supply turned off. So yeah, there's no current limiting going on with this device, and it's warm, I can tell you that. If you aim this under the actual cutting power for any amount of time, this would overheat. So I mentioned it in the last little section too. But this PCB that I mentioned is something I designed. It has a 3-phase closed loop BLDC controller with Hall sensors. And we've got these 2, 4, 6 FETs right here. We've got a A4910 driver, and then we've actually got the Atmega 32M1 that's driving this closed loop controller here. It generates quite a bit of heat, and that heat has to again sink out of the board. And again, we've got our airflow blowing across this whole system here. These FETs are dumping a lot of heat into the bottom of the board. We've got airflow underneath it as well. This, on the other hand, is surrounded by heat shrink tubing, which I don't have. Oh, here it is. This is the heat shrink tubing that is surrounding this, and there's no fan in the chassis, and it's already warm just sitting there at idle. So I think that's going to be problematic too. I'm pretty sure we'll be able to blow this up when we get it in the machine and actually put it on our tester. So I'll show you this tester now, just a preview. We're not going to use it right now at this second. This is called a, oops, sorry. This is called a Prony brake tester, and it looks complicated. It's not. This is a homemade Prony brake tester, and which doesn't affect its capabilities in any way. The way this tester works is you put a large known diameter here, which is this really large device. You basically insert that in there with the collet, and then you've got this cable here, and this cable hooks from side to side, and it goes around said collet, said device there, and because torque is a distance and a force, we know the distance of that. We can measure the force because these are strain gauges that will measure the amount of torque. And if we subtract whatever the weight is on one versus the weight on the other, and the reason there's a weight difference is that we've got this rotating device here pulling the cable one way and pushing it another. So it might say pull 50 pounds on this side and push, you know, or it would still be pulling because it's under load, but maybe only be pulling 5 pounds on this side. So anyway, you acquire it with a data acquisition device. This is the 9233, I don't know, let's see. 37. This is the NI9237. It's a strain gauge device. It measures at 50 kilosamples per second, somewhere around there. Certainly much faster than we need. And basically what you do is you put your DUT on here, and right now the DUT is this specific spindle, which this is a 1/4 horsepower brushless DC motor, and it's basically coupled with a belt drive to this spindle, which I showed previously, and it's driven by the PCB, which I also showed you just a minute ago. This is set up right now for this test configuration. So this hardware, and that hardware. When you want to test the other one, you'll have to take the spindle off the Bantam machine and mount it here, and then chuck this up in there. And when we do that, we'll be able to measure the actual continuous and peak torque. And so continuous, of course, is continuous. So you run it for basically a minute and make sure that nothing catches on fire, basically. And then the peak is basically this armature here pivots, and you basically move your arm here. And the more you pull this down, the more torque it's going to apply. Or really, the shorter this is going to become. So it's going to be pushing against that, and it's more torque. And so with that, you can very, very easily calculate the true power, the peak power, the continuous power, and rather than just take what I imagine they've done, which is multiplying the peak power they were able to measure doing something, just multiplying the current times the voltage, which is absolutely not a valid way of doing it, but everyone does it that way. This Prony brake tester is the correct way of doing it. Another way to think of this device is that it's a dynamometer, just like you would test a car's horsepower with. This is just made for spindle testing. So that's that. I've got this little hacky Arduino Uno here that's just telling me the RPM. So one of the things you want to do is you want to measure the torque at various different RPMs. And so you don't have to do it accurately because you're gathering the data so quickly. After you've gathered all of this data, you can go back and pull out and say, well, at 2600 RPM, I was making 250 watts of power, and that's this much torque. And you can basically, this doesn't need to be accurate at all. You basically take this and you just drop it down slowly, and then you can go and gather all of your data after the fact, and it's basically 100% accurate minus whatever your measurement uncertainty is, which again with this in our hardware is much less than we care about, certainly less than 1%. So we'll get that on there eventually. I need to again be able to take the spindle off this body. I can't test with this Prony brake tester when it's installed in the machine, and I'm not able to take the spindle off right now because this right here, these 4 screws here on these set screws are actually Imperial. It appears they're a 1/16 inch Allen wrench, and until I take those off, I'm not able to eject this spindle. And maybe I don't even need to do that. The other problem is that I need, again, this square drive, which I gathered last night. I ordered it as well. I think it's a 5mm square drive. But I'm still not 100% sure that when I take this square drive out with an impact driver, I'm not sure these rods are ever going to slide free. If that is the case, that's just going to be a huge deal breaker as far as servicing this machine, because it will mean that you can't service the bearings at all, which would be a deal breaker. Now, one thing I didn't point out yesterday either, and I should have, I know the light's bad here, I came off this camera mount, but the bearing spacement on the Z stage here is just not good. Like, it's really, really bad. What it causes is 2 problems. One is that any torque in this direction here is very hard to resist with this spindle, with the Z stage here, because there's just not enough distance. This should be much taller. The second problem you run into is the same thing, but in this direction here, and that's again because these bearings are so close to each other. Any torque you apply in this direction is not going to be able to be resisted very well. It is resisted, but the squaring here, any play you have is much worse. If you were to make this quite a bit further, and which would require you to make the gantry quite a bit taller, which you could do if you turned the stepper here, if you just turned it sideways and belt drove it, you could make this 3 inches taller and not have to change the outer dimensions of the case at all. And that would make you allow you to make this 3 inches taller, which would allow you to have the correct spacing that this spindle head really needs on the Z stage there. But anyway, barring that, you basically have some rigidity issues this way and that way, which are kind of the only 2 ways that you need it on the Z stage. So that's an interesting design decision. Probably wouldn't have made that one myself personally, but yeah, that's where we are. So probably no more updates until I get these tools here in a couple days. I've ordered them online because you can't exactly just go in and buy a 5mm square drive or a 1/16 inch Allen wrench at Home Depot or Ace Hardware or whatever. Those are kind of specialty items. And yeah, cool. That's it for now.